Okay, so we are fast approaching midnight. About midnight, I turn back into a pumpkin, so we're gonna talk fast here. All right, the inverse of a matrix. So, I mentioned in the last video that there is no such thing as division when it comes to matrix operations. So, if I wanted to figure out or determine what A or B is, or if I want to sort of go backwards through an algebra equation or solve something in a different way, and if I want to solve the way we traditionally think about solving an algebra, I often will need things like division, right? If we think about our traditional operations, if I am multiplying something to undo that, as we might say, we would need to divide, right? Those are inverse operations. Well, division doesn't exist, so we need sort of something as a placeholder for the inverse, or to take the place of division in this case. So what we're going to do is we're going to find something that is actually going to cause us to get a multiplicative identity of 1, or to cause our result to be 1. So for example, so if we think about like in algebra, right, if I have 3x equals 9, right, we know the answer is 3, but the way I would solve this is I would divide by 3, and what happens here is 3 divided by 3 gives us the result of 1, right? So it becomes 1, and 1 times anything is itself. Now, in matrices, 1 is not actually a matrix of all 1s. 1 is actually the identity matrix. So the identity matrix is what we can multiply something by to get itself back out. So what we're going to try to do is we're going to try and find some other matrix that when you multiply it with your matrix, your result becomes the identity matrix. So instead of division, we can kind of think of this as, instead of dividing by 3, we're going to multiply by 1/3 instead. The result ends up coming out the same, but it's sort of a semantics issue. But that's kind of what we're going for here. So the inverse matrix, we can only do this, so notice square matrix. So when we're talking about an inverse of a matrix, we're only talking about square matrices. And what we're looking for is something where if I multiply that matrix times this other matrix, what I get is the identity matrix. And so we're going to talk about a couple of strategies for doing this. So the first one is a strategy that uses a 2x2 matrix. So this strategy only applies to a 2x2 matrix because right now we don't know anything else about determinants, and it also doesn't apply to other ones. But we're going to start off by talking about the determinant. So the determinant of a 2x2 matrix is a value that we get by taking the product of the diagonals. The difference of the product of the diagonals. It's a weird way to say it, but we call it the DET of A, and the determinant is A times D, so the main diagonal minus the product along the secondary diagonal. I just crossed everything out there, made it hard to read, didn't I? All right, so pretty straightforward, real simple mathematically. So here's a couple of determinants. Let's see. For A, the determinant of A, I'm going to take 1 times 4. So I get 4 minus 2 times 3 is minus 6, and I get negative 2. Right? Determinant of B, I'm sure you're already way ahead of me on this one. I actually don't even need to do the subtraction. Negative 1 times 3, negative 3, that's 0 times 0, 0. So, hey, ta-da. All right, last thing, the determinant of C. I'm going to take negative 1 times 2 gives me negative 2, minus negative 2 times 1 gives me a negative 2 again, so minus negative 2 gives me 0. All right, so here's where we're going to use this. So there's a theorem that says that first, we can decide if a 2x2 matrix is invertible or has an inverse as long as your determinant does not equal to 0. So first we're going to check to see, does my determinant equal 0? If it does, we have a problem. That problem comes in the fact that we're going to actually take a matrix and divide by that determinant. And if it's equal to 0, we're dividing by 0, which makes everybody sad. So no dividing by 0, which means that if our determinant is 0, we don't have an inverse for our matrix. But if it's not, then the way we're going to find our inverse is by taking 1 over the determinant. So, right, this is the determinant of A here, and multiplying it by the matrix where we flip what's on the diagonal. So on the main diagonal, notice our main diagonal switches, and the signs on the other one, so the C and the B stay in place, but they change sign. So whatever C is, it becomes the opposite sign. Whatever B is, it becomes the opposite sign, but it doesn't move around. Only the ones on the main diagonal are going to move. So if we go back to these A, B, and C diagonals or matrices up here, we can find the inverses. And we're going to actually verify that they are the inverse, but I'm going to let you verify them for funsies. Practice that matrix multiplication that we're getting so excited and jazzed about. But here we go. Ooh, purple. I like purple. Purple's been great. Nice jazzy pop-up color. See, it's getting closer to midnight, guys. All right, so based on what we found in the determinants, A is invertible and B is invertible, are invertible, but C is not. So we're just going to ignore C. We're not going to do anything with it. For A, what we're going to do, so the inverse of A, or the inverse matrix, or the of A, we denote it with the -1. So just like we do when we talk about like inverse functions or inverse functions, we use that -1 exponent, but it's not actually an exponent, it's a notation, right? So that's a notation. So we're going to take 1 over our determinant, so we'll take 1 over -2 times our A matrix, but we're going to flip what's in our A and our D positions, or flip what's along the diagonal. So the 4 goes where the 1 was, the 1 goes where the 4 is. The other 2 stay in place, but they change signs. So I have a -3 in this bottom position and a -2 up here. And I can multiply this out. I'm going to get, so I'll do my scalar multiplication. So I get a -2, I get a +1 here, I get a 3/2 here, and I get a -1/2 here. And there we go. So now to test if this actually is an invertible, the inverse of A. So to test it, we're going to take A times the inverse, and what it should equal is our identity matrix. If it doesn't, something went funky. If it does, great. And in this case, I did test it. It works. We're good. We are golden. Oh boy. Okay. So you do B. Do B. Come on back. See how you did. Had to do. Spectacular. Wonderful. Great. Can't imagine doing any worse. Okay. Again, if you wanted to double check and make sure that this actually is the inverse of our matrix C, we would take B times its inverse, and honestly, it doesn't matter which order you do these in, because they will end up being invertible. These are these are cases where that rule where the order matters falls apart. So these are some of our exceptions to those cases. It doesn't matter what order you multiply a matrix and its inverse by, you should always get the identity matrix. Okay, so we've done that. Now we have a theorem, and here is where we're going to start connecting this idea of matrices and vectors back to what we were talking about in our systems. So if A is an invertible n by n matrix, then for our matrix equation AX equals B, the unique solution to that, so before what we had to do, right, was we set up a matrix where we had A over here and then we had B over here, and we did our row operations to try and find what X would equal, right? Well, now what we can do is, if we can find our inverse, all we need to do is multiply both sides of the equation by that inverse, and we end up with our X equal to something. So might be a couple more steps, really depends on the size of the matrix, whatever. All right, here's the proof. You ready? So some things that we know, right? We know that A times its inverse is the identity matrix. We also know that the identity matrix times anything is that anything. So if I can get the identity times x, well, that's just equal to our x vector, right? So what I'm going to do, so here we have our ax equals b. If I multiply each side of the equation by the inverse of a, and notice the position or the place that I'm doing this is really important. I'm putting that a inverse in front of the b vector because we know that a b vector is only going to have one column. And so our a vector is going to have more than one column. So we need to make sure that we put the vector before, put the matrix before the vector. That's moral of the story. This guy over here, right, we've determined is the identity matrix. And we've also determined that the identity matrix times anything is itself. So bada boom, bada bing, we get this guy right here. All right. Yay! It's beautiful. Absolutely beautiful. All right. Some properties here. You're going to notice these properties are actually really, really similar to the properties we had for transposes. That is, the inverse of an inverse gets back to where you started. Hopefully that makes sense. That seems pretty logical, right? If I take the inverse and then I take its inverse again, all I've done is go forwards and backwards, and I'm back where I started. To take the inverse of a product, I can take the inverse separately and then take their product, but again, notice the order here, right? A times B inverse is going to give me B inverse times A inverse. And lastly, we can combine this idea of transposes and inverses. So as long as A is an invertible matrix, so is your transpose, right? Because the transpose, all that does is switches your rows and your columns. So if it switches your rows and your columns, that's not going to change anything about your determinant. So you're still not going to have a determinant of 0, which is great. So if I take the transpose, or the inverse of the transpose is the same as the transpose of the inverse. Hope that makes sense. Okay. We are so close, guys. So close. Elementary matrices. An elementary matrix is what happens if you perform a row operation on an identity matrix. So you'll see in this elementary, so an E1 here. So it's an elementary row operation because, or an elementary matrix because it is the identity matrix with one minor exception. So you'll see here that this is, we've replaced row 3 by, what did I say? By, we've taken row 3 and subtracted, so this is row 3 minus 4 row 1, right? So if we think about the traditional identity matrix here, we take 4 times the top one and, negative 4 times the top one added to the bottom one. Ta-da! This one here, what we've done is we've switched row 1 and row 2. And lastly, down here, we took row 3 and we multiplied it by 5. That's it, right? Nice, simple, easy row operations. And it turns out that doing these row operations or taking an elementary matrix and multiplying it by a matrix is equivalent to doing a row operation on A. So the product of an elementary matrix and a matrix is the same thing as doing that row operation on A. And we're going to use this idea to help us find the inverse of a square matrix that is not 2 by 2. So we could do this on a 2 by 2, and we're going to actually do it on a 2 by 2 just to show that it works. But what we're going to do is we're going to set up an augmented matrix where on the left side, we'll start with our original matrix, and on the right side, we'll start with our identity. And then we're going to do our row operations until we end up with the identity on the left side and our inverse on the right side. Now, if we cannot get this down to the identity, that means that we do not have an invertible matrix. So if not able to get to I on the left-hand side, matrix is not invertible. So if it comes out to something where you end up with contradictions, or you end up not being able to get ones if your pivot points disappear, whatever, that means that it's not going to be, we can't find an inverse here. All right, so we already know what the inverse of A is from that previous example, right? The inverse of A was -2, 1, 3/2, -1/2. So what we're going to do is we're going to do our row operations here and see if we can get down to and prove that this actually works. So I'm going to set up my matrix. So 1, 2, 3, 4, yay, 1, 0, 0, 1. And I'm going to keep doing row operations. So first thing I'm going to do is I'm going to eliminate that 3 in the bottom position. Gives me 1, 2, 0, -2, 1, 0. Hopefully you're following along with what I'm doing. The next operation I'm going to do, I'm going to try and, I'm going to turn that into a 1. So I'm going to divide everything by -2. Gives me 1, 2, 0, 1. 1, 0, I haven't done anything to the top row yet, but now I have 3/2. Ooh, that's a good sign, and -1/2. So as of now, my my top one is looking good, or my bottom one's looking good. We're close to it, right? Oh, probably would have helped if I wrote down what our inverse was from the previous slide. That would, so we can see if it matches. 1, 3/2, -1/2. All right, okay. All right, last row operation, we're going to use row 3 to eliminate the 2 in row 1. Get 1, 0, 0, 1. Yay, we got down to our identity. And then we get, so 3/2 times -2 is -3/2. It is -3, right? So 1 minus 3 gives us our -2. Ooh, that's a good sign. -2 times -1/2 is +1. So 0 plus 1 is 1. Oh, hey! And we have achieved success. Look at that. It's the same as that. Yay! Whew. So close. I have one more example of, and this video got a little out of hand. And then we have like a 3-second video on the next one. Okay. Here we go. Last example. This guy's a big one. Ooh, ooh, ooh. Okay, we're going to find the inverse of this if it exists. So notice the if it exists part. Again, if I cannot get the identity matrix on the left-hand side, I don't have an inverse possible. Okay, here we go. We're going to set it up. You're going to do the row operations. You're going to come back. You're going to see if yours matches. Okay? All right, so to set this up, 0, 1, 2, 1, 0, 3, 4, -3, 8, 1, 0, 0, 0, 1, 0, 0, 0, 1. So we're always going to put the same size identity matrix on the right-hand side to start with. And now we're going to do our row operations. All right. Do some row operations. Pause the video. Come back. See how you did. How did you do? I had a little fun with some colors. Sorry. Looks like, so I did get down to the identity matrix here on the left-hand side, which means that our inverse exists and is equal to what we have now on the right-hand side. So I got -9/2 in that first position, 7, -3/2, -2, 4, -1, 3/2, -2, and 1/2. So you'll notice, unfortunately, a lot of the time in inverses, fractions are going to happen, even if our original matrix had whole numbers. Hate to tell you, fractions are going to happen. Right? If you also think about, like, if you kind of compare the inverse to being a lot like dividing, often in dividing, right, you're introducing a multiplication by a fraction. So it kind of makes sense that we're going to end up with quite a few fractions in our inverses. All right, that is it about the inverse. The last video today will be, or this week, is sort of a little bit more about deciding if something is invertible. It's a real quick, just bunch of properties. All right, bye.